DC-DC board-mounted power modules, or BMPs, are essential building blocks in modern electronics. They offer high efficiency, compact form factors, and modular scalability. But their internal architecture, especially the use of high-speed switching and planar magnetics, makes them inherently noisy. In this video, we'll explore how to identify EMI sources in DC-DC BMPs and apply proven strategies like shielding, filtering, and layout optimization to mitigate both radiated and conducted emissions. EMI emissions begin with a source, often a switching converter, emitting noise at fundamental orthoharmonic frequencies. This noise can affect almost every component in your system, and some victims may even retransmit the interference. DC-DC BMPs use planar transformers and inductors, often built into the PCB with open magnetic cores and windings. These components act as antennas, radiating noise at switching frequencies which are typically 100 to 500 kHz as the fundamental frequency and the associated harmonics, which can extend into hundreds of megahertz. The radiated EMI is strongest in the vertical direction, affecting components placed above or below the module. To reduce radiated EMI, use BMPs with grounded baseplates to block emissions from the top. Add a large copper ground plane beneath the module on the host PCB to absorb and redirect EMI. While six-sided metal enclosures are seldom used in BMPs, system-level shielding components and kits can be used to contain emissions effectively. Conducted EMI appears on the input pins and must be filtered externally to the module to prevent interference affecting other devices sharing the same power source. Key components include common mode chokes to suppress differential and common mode noise, RC snubbers to dampen high-frequency ringing, low ESR capacitors for effective high-frequency attenuation. Filter design must match the BMP's switching frequency and power rating. Effective filtering starts with selecting the right components. Choose inductors with appropriate saturation current and low core losses. Use capacitors with low ESR to maintain high-frequency performance. RC snubbers should be tuned to the switching frequency to suppress ringing. To effectively manage conducted EMI in board-mounted power modules, Advanced Energy provides a reference filter design tailored specifically for BMP modules, optimized based on the module's switching frequency and power rating, ensuring compliance with 55032 EMI standards. To further enhance performance and ease of integration, Advanced Energy also offers the AIF Case Kit, a robust metal casing solution with EMI shielding and an insulator sheet, designed to improve radiated EMI performance and protect surrounding circuitry. PCB layout is as important as component selection. Even with good components and filters, poor layout can compromise your design. Common mistakes include overlapping power and ground planes. Long traces act like antennas and invite EMI. Sharp 90-degree trace corners causing reflections. To reduce EMI through layout, separate power and ground. Use orthogonal routing between layers. Minimize trace length and loop areas with tight capacitor placement. Use angled corners, which helps the signal flow more smoothly. Avoid stub traces and ensure short return paths. At high frequencies, noise takes the shortest path. Poor trace routing can bypass decoupling capacitors, weakening EMI control. Clean and direct traces help capacitors work better and reduce the need for extra filters. In this example, we'll explore how a simple PCB layout correction can dramatically improve EMI suppression. Here's the first layout. Notice that due to the capacitor's top connection, it is not fully engaged and active in the circuit. This reduces its effectiveness in shunting noise to ground. Cutting a trace and rerouting it correctly activated the decoupling capacitor, reducing noise by 15 dB. This small change in layout allowed high-frequency noise to be properly diverted to ground instead of bypassing the capacitor. Even though the physical distance was only around 10 to 15 millimeters, the impact was significant. It highlights how even minor layout decisions, like trace direction, can influence whether a component actually performs its intended EMI suppression role. Ultimately, the goal is to ensure the final application meets EMI compliance. This is achieved through two main strategies. The metal casing of the product provides shielding against radiated noise, while the EMI filter suppresses conducted noise at the input. Together, these elements form a complete EMI mitigation system.
Managing EMI in DC-DC BMP modules requires a combination of shielding, filtering, and layout expertise. With the right strategies, you can ensure your system meet compliance standards and perform reliably in demanding environments.
Advanced Energy's FAEs provide hands-on support, proven filter designs, and layout best practices to help you reduce EMI. Learn more on Advanced Energy's website. Visit www.advancedenergy.com or contact us at powersales@aei.com.